Hi, my name is Justin Shi, and the presentation title of my paper is TOI CHAIN, a proposal for high-performance temper-resistant transactions without scaling limits. I'm with SMC Labs, and also I'm with Temple University. And here's outline my presentation. We start with the motivations and why transactions are important, and what we're trying to do is try to make things in parallel. Transaction in parallel is a pretty controversial topic, but it can be done. And then we're going to show scalability, how a parallel system can scale indefinitely. And then we go down to the bottom and see how technology, what did we introduce to make this infinite scaling possible. So we introduced ACAN, stands for Active Content Addressable Networking, which is a protocol, and also a kernel extension called SMC, Static Multi-Computing Computing Kernel Extension, and for blockchain. And then we will present the main topic of a TOI chain and going through protocol layers, how we can sandwich the ACAN and SMC layer in between the consensus and the peer-to-peer networking layer and TCP layer. And then we briefly discuss smart contracts and decentralized application and temper resistance. And those are inherited from the existing code. And then we talk about energy efficiency and why we can be more efficient than other chains and self-optimization features that I will bring to the table. And then we will actually explain in this TOI chain example, the project is only a experiment to demonstrate how re-engineered in service infrastructure can get rid of the scaling limits. And the same can be done for all the service infrastructures. So therefore, we have a broad impact section. And then we go through summary. So transaction processing is a timeless cornerstone for all sub infrastructures. And blockchain experiments, the blockchain experiments expose the foundational weakness of existing transaction systems. And that's why a lot of people are interested, especially financial institutions. So blockchain-inspired distributed ledger technology, which enable DeFi, decentralized financial applications, which is running everywhere. And there are two principles for building these systems. Number one is the infrastructure must be zero single point of failure. So blockchain system can deliver that without much effort. And for traditional database systems, you have to use some other means. And the second feature, and the second principle, is that this infrastructure has to be infinitely scalable. So legacy systems using data partition to achieve the goal, but by introducing more vulnerability of a single point of failure for the entire system. And the capacity is also increased that same way. And then you have something called the scalability dilemma. So we'll go through this in this presentation today. First is a zero single point of failure. And it's very simple to say, it's hard to do. All blockchain systems can offer this without effort. Okay, except for the one chain is called Solana. And then, it doesn't have a single point of failure. And it did have failed. It did fail multiple times. And traditional transaction systems, however, and can mitigate the single point of failure by using either synchronous or asynchronous transaction replication. But neither can meet the real-time requirements. And performance and capability scaling is also a sore point for blockchain. So blockchain offers immutable ledgers. By definition, the ledger cannot be changed. So you're passing many transactions and your ledger is growing. So there has to be a limit how big the ledger can grow. So you have to have a technology offer unlimited storage. Otherwise, the chains, whatever running today, will eventually stop when everybody's storage is exhausted. And then the system must deliver consistent delay regardless transaction volume. So the current system really can't do that. So traditional database has a better time. And traditional database uses data partition You have a single server is not good enough. We have multiple servers. So we chop the data into 2 pieces. Okay, we distribute the load, but we introduce more single point of failures. So therefore, we have caught between rock and hard place, and the term is called scalability dilemma. Do you want performance or you want reliability? So you have to choose. So it's not really fun game. So we cover the motivation, and the idea is to make things in parallel. So the motivation is that it has a really hard facts in front of it. So we have to acknowledge all networking processors and storage devices have finite and unpredictable service life. So each component will eventually crash. We just don't know when. And the transaction volume is unpredictable. And you cannot say my system can only process in 5,000 transactions per second, because it could be 20,000 for next moment. So therefore, all transaction processing infrastructure, it must be processing the transaction locally, but replicate the same thing elsewhere. It must be done, otherwise it's not reliable. And it must not have any single point of failures. And also can scale indefinitely. You can scale any size you want. Okay? And then it has to be temporal resistant. But traditional database really can't do that. Okay? Because you have admins. So admin can see everything, can compromise everything. Okay, if it's on the wrong foot. So even if code is open source, and you have to provide temporal resistance. So blockchain does this very well. So system repair. So infrastructure will deteriorate over time. Okay, hardware will go slow and the software runs slower, and hardware actually burn out. And the system repair and updates should not stop service. So blockchain system can do well, but the database system have trouble. But if all these are required for trustworthy sub-infrastructures, and I don't think there's a much debate about these. These are the pretty hard requirements, but hard to get. So current industry standard is synchronous or asynchronous transaction replication. But I put that 1 + 1 as the 1 here is because neither can deliver positive improvement. And there's always a dilemma. You add 2 process, you deliver less than 1 process performance, less than 1 process availability, because the probability is working against you. So for asynchronous replication, you have a primary server, server 1, you have a second server, server 2. Anything committed on server 1 will be eventually replicated on server 2 asynchronously. On surface, it looks fine. But when either of the server or the queue can arbitrarily crash, which will happen, and then you lose transactions, and you don't know what get lost. So some of you are familiar with the financial institutions that will probably argue and say, hey, we have a banks using database for years, ages. I never had this problem, never heard people talking about this. So banks solving this problem using legal means. Okay, if you check your balance every month and you find you lose any transaction, as long as you have a reliable receipt and bring to the bank, a bank will refund your money, and with penalty, honestly. But if you don't, so the funds will belong to unclaimed freight. Okay, so it's a known fact, but not many people are aware of this. Okay, for single replication, there's no transaction loss, but it is a severe penalty on performance. So therefore, single replication is only installed on slow transaction systems for messaging, for mission critical messaging systems, and so forth. So current transaction systems are sitting ducks on the network because they have a well-known address, and everybody does know where they are. Client server, right? We know the server address and have to go there. It doesn't matter how many aliases you create, and DNS will eventually resolve into the IP address, and then you can attack it. So it's a sitting duck for DDoS and ransomware. So these are the known facts. The culprit actually is deeper. It's in the program paradigms. So the number one fallacy in distributed computing is assuming that network is reliable. The problem is that this assumption is baked in all popular programming paradigms. That includes remote procedure calls, remote method invocation, and a message passing interface, MPI, which is popular everywhere. So the consequence of these paradigms is producing infrastructures have unavoidable. So you already have a single point of failure. Not only one, you have many. And then transaction retransmission is never talked about. It's a void. How did we get here? It's because client-server programming paradigm. Because we teach that in all universities and technical schools and the high school even sometimes. Okay, but the server-to-server programming is absent until the emergence of blockchain protocol. Now, when I say protocol, is a server-to-service programming has to be coded as a protocol. Otherwise, it's not a service because server has to be stateless. Remember that? So lesson from blockchain experience. Blockchain has done a great job. Okay, so it demonstrated you can have a zero trust. Even if you let it code in open source, you cannot break in. Temper resistance also allowed maximum available services, regardless service up and down, and your service is always available unless all servers shut down at the same time, which is unlikely to happen for Bitcoin and for blockchain applications. The second unique feature of blockchain applications, the protocol, is decentralized conflict resolution. In blockchain terms, it's called a double spend free. So a coin or a fraction coin. Now see how you can figure out how you can figure out which fraction of the coin can be double spent. Okay, it's a non-trivial challenge, isn't it? Using something called a consensus protocol. So the trouble of these protocols is they're slow. Using proof of work, which is a Bitcoin case, and it's energy intense. It takes so much electricity to mine the coin. And of course, you pay handsomely. And for proof of stake, on the other hand, you save 98, 99% of the electricity, but you're risking a decentralizing risk because you have to use the staking pools. People actually pledge money together and they mine this transaction together, and they're risking of a 51% attacks. So the large mining pools can overtake the entire network potentially. And there is also the growing ledger concern because ledger is growing every day. If you look at the chain logs, you can see that transactions are actually processed every day, every single minute, every single second, and the ledger grows single dimension. Okay, so it keeps on growing. So without answering infinite scaling, and you have to face technology uncertainties, and it's a scalability challenge, and it's a very common problem. So what we bring to the table is a new protocol called the Active Content Addressable Networking. The idea is to allow any computer to contribute what it knows and from anywhere, anytime on the network. So it's a key value pair tuple space abstraction. So supporting three protocols: put a tuple into space, get extracted, and or read it, and leave the tuple in place. So with these three protocols, it carries two missions. It allows the process to communicate with data, with other processes, and also automatically synchronize. So pictorially, and it looks like this, but it makes more sense if I plug into a statistic multiplies computing kernel for the local operating system to offer local resources hardware-wise, and to offer the local resources to satisfy the computation needs. The tuple space came through and said, I need the two processor, I need the three processor, and I happen to have 15, so I'll give you several. Okay, so with two together, we enable automatic data parallel processing. So the topology of a parallel processing like SMD, MID pipelines will automatically form at runtime. You don't need explicit part begin, part end, parallel begin, parallel end. You don't need any of this. And we're exporting all available resources automatically. So now with a parallel system in place, assuming that I can do what I said we can do, and how do you prove it can be infinite scaling? So this problem is also well known in the community. And first of all computing tasks can be done either in parallel or in sequential. Either way, any computation task can be done either parallel or sequential. For parallel system, the scalability measure, we have two laws. One is called Amdahl's law, and in literature is called unscaled speedup, which in my opinion is misleading. And there's also Gustafson's law. It's called scaled speedup. Again, it's misleading in my opinion. So, but this has been confusing the community for ages. But in general, and very few people actually believe anything can scale indefinitely. Okay, but that perception actually is incorrect. So let's dive into the little mathematics. Introduce a little mathematics. Introduce a single variable, which is x, fractional between 0 and 1. Okay, and x represents the percentage of sequential instructions has to be done in sequential. Okay, cannot be done in parallel. So 1 minus x must be the number percentage of instructions can be in parallel. Okay, so therefore your speed up according to Amdahl is 1 over, which is 1 is just everything sequential. And the bottom part is the part that cannot be in percentage, cannot be done in parallel. And a part of that can be done in parallel, but accelerated p times. So the ratio between the two is just speed up. So pretty obvious, very straightforward formulation. And this has been existing since 1967. Okay, it's a long way back. Okay, 1988, a gentleman whose name is John Gustafson, who had a parallel machine running on Department of Energy applications. Okay, so there's a measure of a sequential instructions done in sequential and a parallel instruction done in parallel, but running on P processors. So you measure how many sequential instructions running on P processor, also measure how many parallel instructions running on P processor. So he got X prime. Now the speed up for Gustafson's formula is 1 minus X prime, which is the time that a percentage of instructions that are done in parallel. Okay, this is parallel. The sequential part it didn't have measure, so I have to reverse engineer. Take the X prime, multiply X, that's the sequential part. So the design of this formula is when you add processors, and then you can get a better speed up. But just hold a second, just think about this equation just for one minute. What does it mean by adding processors? You're adding processors really solving bigger problem, isn't it? So the problem size is missing in this formula, in both formulas. So once we bring the problem size into the discussion, and then everything becomes clear. So we're scaling 1, and I take p to infinity, and this speed up converges into 1 over x, which is a picture on the right side. Okay, but you cannot scale p to infinity because it's undefined. You cannot scale p without changing x primes. X prime will change when you're actually changing p. So if you are careful, you translate x prime to x, and then you find out the x, if you're solving big problems, and your x, the serial percentage, actually is asymptotically diminishing, approaching to 0. So 1 over 0 will give you infinity. So speed up can be infinite. But this discovery should not be surprising. Okay? Maybe some of you will find it surprising. This means that every parallel application is infinitely scalable, as long as other dependent overheads like communication, synchronization, and the security, handshakes are not overwhelming. And transaction systems are supposed to handle any number of transactions, so there's no upper bound. So therefore, any properly designed transaction planning system can scale and should scale indefinitely. And this is actually being practiced every single day. So to convince you is if you check on top 500 supercomputer benchmark, you see everybody's competing. Say who can solve bigger problems using more processors. There's no limit on no process. There's no limit on size of problem that it can solve. So as long as you can demonstrate you can solve bigger problem, and you win. And then all production database systems today are the living proof of infinite scaling. It's just you're losing reliability. So the challenge is how you get the performance and reliability at the same time. So that brings us to introduce you to ACAN. So how we can bring ACAN, the active content addressable networking, to a blockchain protocol, and put the runtime also put into blockchain protocol. Now here's a slide of blockchain protocol layers. So on the left side, and you can see the typical blockchain layers. You have a TCP/IP, and then you have a peer-to-peer network, and you have a consensus protocol, and then you deliver the network with an immutable ledger. On top of that, you can have enhancements called the layer 2 protocols, like Lightning Network. So you can do a lot of off-chain processing and only store the final result on the chain. And you can do cross-chain bridges, and you can do decentralized applications like games and stuff. And you store you manage your own off-chain transactions and store the results into the chain. So those are the things called the high-level layers. But what we do is we sandwich ACAN and SMC in between the peer-to-peer network and TCP/IP. So the idea is to bring you to a TOI chain. Now I have one exception here. Is why is TOI? What is TOI? TOI is a NASA recently discovered planetary system. Has its own habitable zone. So it's bigger, 1.5 size bigger than Earth, and it looks like, from NASA data, looks like potential human livable space planet. Okay, and then it so happened that TOI has a French pronunciation called toi, which means you. So we're gonna bring a very remote future planet into you. So that's the analogy that I would put in the name. So it's like a marketing gimmick, but it's kind of fun. So the TOI chain, or TOI chain, is a proof of stake protocol plus ACAN plus SMC, and put all together it's called TOI or TOI. So this is the system architecture of a TOI chain. So you have we don't use a lot of electricity, and we allow anybody with a machine, with a cell phone, you can mine coins. You have a storage, you have a terabytes of storage, and you want to share half terabytes with everybody else, and you get paid. So you can earn passive income by using your unused resources. The benefits is a dramatically improved performance via parallel processing, and the temporal resistance is maintained. And a cryptographic proof rigor is still there. And the storage becomes infinitely scalable. And by controlling the replication factor, because ACAN, we control how many replication of your ledger should be. So nobody needs 17,000 copies of ledger, do you? So it's the protocol itself, the simplicity of protocol development because of ACAN is dramatically simpler than any other ways. And then we allow programming data to be completely coupled from physical devices. So your protocol and the data are completely decoupled from a hardware. And non-stop service become possible under arbitrary failure conditions. So if you have a solar flare on, say, certain hemisphere of the Earth, and the other half will still operating. So unless you have an entire network shut down, or every process die at the same time, and you have a service up, just very much like a Bitcoin today. So adding resources can meet any processing demands, and non-stop service in real time network maintenance is possible. So we can maintain a network without stopping service. So all these, this is a colorful slides, and you can see these are the temporal resistance, high performance, high reliability, high security, and infinitely scalable. So which means the coin you put into the TOI chain will be there forever. So it's you can call it digital gold, and this is a real digital gold, and it will never disappear. So then we can spend a little time on smart contracts, and this is where the hacking, the pain of a cryptocurrency actually is. It is because smart contract is an extension on the script engine of the protocol. So each blockchain protocol has a script engine implemented. It's software, and it's a compiler interpreter and execution engine stack machine, and will actually execute the scripts. We call it smart contracts. So the problem of this smart contract is in the design. If we design the language smart contract to be Turing complete, which means it includes loops, and then somebody gonna exploit it. Okay, somebody exploit it using the loops to drain anyone's about the target's account. Okay, so this is what happened, has happened numerous times, and it continue to happen. SMCL is a smart contract language for TOI chain. So it's non-Turing complete. So therefore, you cannot drain people. So only execution once and stop right there. If you want to repeat it, and you have to run the same script twice. Okay, then you can have a dApps easily built on top of SMCL for new application, and then with the POS consensus and ACAN and SMC, and we enable the most energy efficient processing against other chains. We compete against other chains. Therefore, we can reduce the transaction fees. So it'll be lowest fee possible. So TOI chain is only experiment. We're going to demonstrate what we can do by re-engineering an existing blockchain protocol to make a scaling free scaling. So there are more applications. So all existing multi-core, multi-processor, and the cloud services can be re-engineered to eliminate scaling limit by shifting the paradigm into a non-flawed paradigm, because you don't have IP address hard-coded into your production software. So re-engineered service has a potential to harness multiple quantum computers because of infinite scaling. So here is a chart showing you the potential things we can do for fintechs and the W3 infrastructures, advanced applications. That includes deep space probes and nuclear power plant monitors. So anything real-time, multi-processor, non-stop service, and infinite scaling, and we can meet that demand. And physically, how this can happen? Because you see, AK and SMC crypto actually all called protocol, the part of protocol. So they run these programs running all machines, right? So like a TCP protocol, TCP/IP protocol can be embedded into hardware as a FPGA or ASICs, and they can plug into hardware and then make a seamless transition into state-free, scaling free infrastructure, and in a much better performance and a cost effectiveness. And we can also deal with GPUs. So we can put the AK and SMC crypto into mods and plug into GPU cards and make a GPU cluster not failing, because GPU has a known problem of short meantime failures, especially for high core GPU cards. So people familiar with GPU cards, and we should understand what they're talking about. So in summary, transaction processing is a timeless cornerstone of all cyber infrastructures. The legacy client-server programming paradigms are flawed for service-to-service programming. It's not flawed for client-to-server programming, but it's a flaw for service-to-service programming. So blockchain protocol demonstrate fault-tolerant, tamper-resistant, but resource-inefficient service-to-service programming. What we bring to the table is we make the paradigm shift is a resource-efficient service-to-service paradigm with temporal resistance for current and future service infrastructures without scaling limit. So with that, I want to bring the acknowledgement. I want to thank anonymous reviewers for their constructive comments and suggestions, and the financial support from National Science Foundation, TOI Association, and SMC Labs are acknowledged here. Thank you.